Double slit experiment. This was done in the early 1900s. Okay, 1912, 1914, 1915. You know, that sort of thing is when quantum mechanics really was born. So it's the early 1900s. So you see, we're almost 100 years away from that now. Okay, and in the 5 or 10 years after these experiments were done, it's my opinion that physicists understood the nature of reality better then than they do now. Okay, so we haven't actually gained much ground in all that time. Now we've gotten a whole lot better about computing. You know, the quantum mechanics of today is far superior to the quantum mechanics at that time, but that's all about computation, not about understanding what reality is like. So today, quantum mechanics is seen by physicists as weird science. Science that nobody really understands. And what's worse yet, nobody ever will. You see, it's that sort of thing. That's because they've thought about it and argued about it for a lot of years with no progress, so they figure that it's an unsolvable problem. It's just weird science. It's just like that. In fact, it's actually very, very simple. It's not a hard problem to understand, and it's easy to predict the outcomes of the experiments once you understand how they work. So I'm going to first just tell you what the double slit experiment was, and then we'll see why it works that way and what it tells us about reality. That upper picture shows the two slits. That's what we have up there, and there, a barrier with two slits in it, two holes. And what happens is that for 100 years or 50 years at least before they ever did the double slit experiment, people had been shining coherent light at slits like that and coming up with patterns like this. Those little white circles in the patterns. You notice the biggest white circle is right in the middle, and the next one on either side is a little smaller, and the next one on the side is even smaller. That's called a diffraction pattern. And the amplitude of that diffraction pattern is this wavy line that goes like that. So that's the screen. That's where you collect the particles. So you throw the particles in on this side, and you get the particles rearrange themselves into this diffraction pattern. Now, that was particles. It started as waves. Okay, and as waves, they understood this, because a wave coming at these two slits, you know, it's a wavefront. You have this like a water wave, right? This thing works with water as well as it works with light. You know, it's waves. Waves come to the hole, and when they get to these two holes, some of the waves go through hole 1, some of the waves go through hole 2, and where you have hole 1, you get new little circular waves coming out of hole 1, and new little circular waves coming out of hole 2, right? Well, what happens then is those two little circles run into each other somewhere in the middle, and when they do, they interfere. So see the little, I really could use a stick, see the little triangle that I have between these two, right up there, down there? Okay, what that says is that's the path difference between things going through those two holes. So something that goes through the upper hole and goes to that point has a shorter path than the one going through the bottom hole up to that point. You can see that bottom part of that triangle is longer, right? Well, when the difference between those two paths is exactly a wavelength, then here's the wavelength. That's what you see in the upper corner. See those two wavelengths? The highs and the lows meet together. The high comes with the high from this hole, gets a high from that hole, and a low from this hole gets the low from that hole. So the two are in phase, is what that's called, because the distance between that shorter distance and that longer distance, the difference in that distance is one wavelength, or two wavelengths, or three wavelengths, you see? Then they always will be in phase, like in that upper extreme right-hand corner. The waves will be waving together. Now, if the difference in those two lines happens to be a half wavelength, then the peak of one falls right on the dip of the other, and they cancel. That's why you get nothing between those spots of light. Okay? So that would be 1/2 a wavelength, 3/2 a wavelength, right? 5/2 of a wavelength, some odd number halves of wavelengths, difference in the paths would show you these holes. So when they come through the two holes and end up at that middle spot between them, those two distances would be equal, because now you have an equilateral triangle, right? They come from a two hole, you go right to the spot that's behind them. So they'll always be in phase, so you get a bright spot right there. And that's the biggest bright spot. And then the next black spot is a half wavelength difference. Then another half length is a whole length wavelength difference, and that's your first light spot. So you see, you kind of get the idea how that's working. That's a diffraction pattern. Light, water, all sorts of waves do it. It was a well-known pattern. Well, what happened is then that Einstein, with a photoelectric effect, said light comes in little discrete chunks of momenta. That means light acts like a particle. We called the particle a photon. And that confused everybody, because up until that time, everybody was happy with light being a wave, because you shine a coherent light on those slits, you get a wave pattern, just like with the water. So we knew light was a wave. Now, light was shown to have discrete chunks. See, waves are just continuous, right? Energy should just be delivered continuously as the wave impacts something, and Einstein said, no, it don't work that way. We get discrete chunks of momenta from light. They're photons. So then they said, well, how can they be photons if they're a wave? See, they were logically incompatible. So they rigged up an experiment, which at that time was very hard to do, that could produce just one photon at a time. And they said, all right, we're going to figure this one out. We're going to shoot one photon at those two slits and see what happens. What they expected to happen was that they would get a bright spot right behind each slit. You get a spot on the screen behind each slit, because the photon would go through, hit that spot. Now they knew when they shine light as a wave, they're doing millions of photons, right, all at once. And then they know they'd get this diffraction pattern, because they'd done that before. And it was like, how does that work? What happens with millions that doesn't happen with one? One's got to make a spot. We already know millions make a diffraction pattern. You know, scratching the head. Didn't make sense. So let's do the experiment and see what happens. So they did. And they sent one photon at a time, and then another, and then another, and then another. After they've sent hundreds of thousands, but one at a time, they looked at the screen and they had a diffraction pattern. It didn't make two spots. How did that happen? How can a particle go through a hole and then distribute itself in a diffraction pattern? Very big mystery. Okay, so at the time they said, well, there's something really funny going on at those slits. Okay, let's see what's happening at the slits. So they created an apparatus that could detect when a photon or an electron, it's easier with electrons because they have charge, you can detect them easier when they pass, or some other particle. We'll make a detector that doesn't interfere with it, but I'll know when one passes by. Okay, so they did that. They put a detector at each slit, and they detected, went through this top slit, this one went through the bottom slit, et cetera, et cetera, et cetera. And after they did 100,000 of them, they had two big lumps, one behind each slit. Finally acted like the particle they thought. They said, okay, let's turn the detectors off. Maybe those detectors are doing something to it. Let's turn the detectors off. So they turn the detectors off, and they get a diffraction pattern. You say, well, this detectors seem to be making it either a diffraction pattern or the two slits. It's something about these detectors. So then what they got to next is they say, well, let's leave the detectors detecting. They eventually got to this point. I mean, I'm skipping years and skipping experiments and all sorts of things, but they eventually got to the point where they realized that they could leave the detectors detecting, but not collect any data. Because the idea was that in the act of detecting, you're actually exchanging energy with the particle somehow, and you're affecting the particle when you detect it. So they detected. Every particle was detected, but no data was taken. So they still didn't know which slot, which hole that the particle went through. Well, what they found out is that they got a diffraction pattern. Didn't have anything at all to do with the energy affecting the particle from the detector. What it had to do with was the information that they collected. If they had information about which slit it went through, they got a pile of electrons behind each hole. If they didn't have any of that information, they got a diffraction pattern. Now everything was even more complicated, right? So they realized that it was the information. They jumped to a couple of conclusions that weren't quite right, but close. One was, that's why they called this the measurement problem. If they made a measurement, they got a particle. If they didn't make a measurement, they got a wave. So they thought up something like the Grinch, they thought up a lie and they thought it up quick. And that was that light is both a particle and a wave. They called this the principle of complementary principle, that light was really both. Sometimes it acted like a wave and sometimes it acted like a particle. Well, of course, rationally we think about this, it doesn't really compute, does it? I mean, it's both, and sometimes it does this and sometimes it does that. But that was, if you take an old textbook in physics, you'll see the principle of complementary is that both ideas of light as particles and they don't really conflict with each other. We don't have a conflict here, people. We just have a complementary ideas about light. Yeah, right. They had a conflict and they just didn't have any idea why it acted this way. That was their way of dealing with the conflict. Well, people do that, right? If you can't come up with something, you kind of find a way to gloss over it. So that was the way that worked. Now it got even worse, though, because this was just your normal, what I've explained to you is your normal double slit experiment. It got even worse because they realized that they could collect the data. So now they've got this one particle at a time coming to it. They're going to collect the data. And they've done this before, and if they just collect the data, they know they're going to get two spots, one behind each slit, because they've collected the data, which slit it went through. Now they have information. Okay? But they didn't look at the screen. The screen was not looked at. Okay? They collected the data. The screen was full of data. So the screen collected all its data. Here the screen was, and it got all its data, just nobody looked at it. It was, still in the computer, or they didn't develop the film yet, or whatever it was. It just was not looked at. Collected data, they expected two spots. But before they looked at the screen, they erased the data. Okay, we collected it, now we erased it. Surely we collected the data, we should get two spots. But if they erased the data before they looked at the screen, they got a diffraction pattern. If they looked at the screen before they erased the data, they got two dots. Now, that's called a delayed erasure experiment. And if you look up double slit and then look up delayed erasure, you'll see it. It's there. And the reason it's delayed is because you don't erase the data until after the experiment's over. The experiment's over. The screen, the film has been exposed. It's collected the data. You've taken the film out of the camera. You just haven't developed it yet. Experiment's over. Now you destroy the data. Now you develop the film. It's a diffraction pattern. You see? So that's why it's a delayed experiment. They could find that even after the fact of the data being taken, if they erased the data, they'd always get a diffraction pattern. If they didn't erase the data, they'd always get two dots. And that made them that's where it got its name as weird science, you see. So that's the famous double slit experiment and then the delayed erasure. And these experiments have been done thousands of times. Probably every physics department on the planet, somebody has done this. It's these days it's an easier experiment to do, but it still takes some money and some time. Somebody's got to invest probably a few $100,000 to set up all the equipment and do the stuff and do it really well. It's not like something you're going to do at home. It takes some good, careful experimenting to do it, good equipment. But it's a common experiment. It's not like, oh, these are just bogus results. They've been duplicated, is what I'm saying, thousands of times, thousands of places, and this is the way the world works. Okay? It's like that. And they say, well, it's like you're going back in time. How did you change that from 2 points of light? It must have been 2 points of light on that film before you erased the data, because we've done that experiment a lot of times. We've taken the data, we exposed it, we developed the film. There's always 2 dots there. So I know that's going to be the outcome because I've done it lots of times. Now this time, the only difference is that before I developed the film, I erased the data. How could erasing the data change what's on the film that happened an hour ago, last week, a year ago? Doesn't matter. Time limit isn't important. A century ago wouldn't make any difference. If a century ago you took the film and only today you erased the data, you still get a diffraction pattern. You see? So they thought that somehow it was changing. Doing erasing the data was making what was on the film change. Of course that doesn't happen. That doesn't make sense either, right? Doing this isn't going to change what happened. What happened has already happened. The answer to that was that what was on the film that nobody had looked at, that hadn't been developed yet, was just probable. There wasn't anything on the film yet. There's nothing on the film until you make the measurement, which means until you develop it. When you develop it is when you get something on the film. That's when the data stream has to send you something. You've developed the film and you look at it, that's a measurement. The data stream, the system has to tell you what's there, and it does that with a probability calculation. That's what we said. So there's really not anything on that film yet, for sure, because the measurement hasn't been made yet. See, that's hard to wrap your mind around, right? That's the way. All right, now we go to this next slide.
The cut question would
Where?
For me.
You have a question, yes.
So at the point of release, don't we know, like wherever you release a particle from, not where it hits the first grain or the first slits, where you release the particle, don't you know that it's a particle? Isn't that information available?
No, it's releasing a particle is not the same as like shooting a BB. Okay, when you fire a BB, you know when you fired it, and you know where you've aimed it, and you know where it is. Okay, that's not the case with these particles. With a particle, you're heating up some element that shoots off electrons, and that's a random process. They just boil off as they get energy from the heat, and then get enough energy to escape their connection with the others, and it's just totally a random process. You can't see these particles. They're invisible. They're too little, you see. So randomly, particles go, and they go not all exactly in the same direction. There's some of them a little bit this way and some a little bit that way. So some of them go through one slit, some of them go through the other. Some of them probably hit in between. You're kind of spraying things there. Well, the whole point of it, and you're actually getting to the next slide, is that there is uncertainty in the position. Because there is uncertainty in the position, then there's a probability that they could be anywhere within that uncertainty. You see? So the probability function is wider, but I'll get to that in the next slide. You had a question.
My question was that to know you had one photon, you had to measure it somehow, whether or not the probability of when it would be shot off.
Well, what they do is they develop these days, they have lasers. They do this with lasers now. In those days, they couldn't. In the old days, they took a light source of some sort, and they took it very far away, and it's a very dim light. And they could calculate about how many photons were randomly given off in random directions, right? So this will produce, 1,000 photons a second, and they're being thrown off randomly, all directions. Okay, then they could calculate that only the probability that one of them would happen to go in this direction and hit the slit. So they'd make it far enough away with a dim enough light that they could statistically come up with the answer that they were only going to get one at a time there. The probability of getting anything more than that was too low. So that's how they did it in the old days, just by removing a source, a distance, and having a very dim source and calculating that they would only get one particle at a time. Now they've got lasers that they can so sensitively pulse, that can actually fire like a photon at a time. But still, there's uncertainty in exactly when that photon comes and where it is. Everything, you know, it's not, making light is a random process of having electrons drop from one shell to another in an atom. At least that's the way it's probably taught to you, that's the way it was taught to me. It doesn't really work that way, but that's a model called the shell model of atom. And because electrons are jumping quantum levels, they emit, they go from a higher level to a lower level, they lose energy, they emit a light, they emit a photon, some kind of a light wave. Okay.
It was never really measured.
So it's not, no, it's not that they fire the photon and they know it's traveling just along this path and it's just going to be here. There's always uncertainty around these particles because they're invisible particles. You don't know when they fire, you don't know exactly where they're going or how they'll go there. These things are so tiny. So even if you look at a laser and you say, well, that laser's just got a little tiny beam, to a photon, that little tiny thing that we see, it's only a couple of millimeters in diameter. That's huge. You know, that's like hundreds of miles. You know, photons are so small that we can't make a tube that's a photon wide so we know they're just going that way. They always have lots of room to go different directions.
Same thing with the buckyball. You mentioned that these experiments.
Same thing with the buckyball.
Yeah.
So the buckyball, you know, we don't see those either. But they know now that part of the experiment is that there has to be uncertainty around, you know, the object that you're throwing at it. That's why it works this way. If there were no uncertainty, then you'd be measuring the particle. You've already made your measurement if there's no uncertainty as to where it is. So uncertainty is part of the experiment. Okay, I'm going to go to the next one. Now, here's really what happened. That was just what happened, but here's the way it works. This is now what quantum mechanics was birthed because of this experiment. And somebody decided that the only way they could get the right answer was to assume that that photon really wasn't a photon, but it was a probability. And here's I'm showing the probability. That's probability versus distance. That means we don't really know where it is. We think it's most likely in here, but there's a very small chance it could be out here and a small chance it could be over here, but it's mostly kind of around here, but we don't really know. Okay? And this is now quantum mechanics assumptions. So this was the assumption. Okay, let's treat the problem this way, and they found they could get the right answer. So we'll assume that the photon is really a probability distribution and not a particle at all. The probability distribution gets to the two slits. And because it's a probability distribution, there's some probability going through one slit, some probability going through the other slit. So the probability goes through both slits. A particle can't go through both slits at once, but probability can. So the probability gets over, and it does just like the waves did. It interacts with itself, and you get the diffraction patterns. Okay, so that's the way it works. So now, this little curve I have over here where it goes, you know, a little bump over the first source and then a bigger bump and then a bigger bump and a smaller bump. Okay? That now looks like a probability distribution. Each one of those bumps is a measure of the probability of it hitting at a particular place. So it has the highest probability of hitting there in the middle, you see, because it's got the biggest peak and the next biggest peak. So you've created now a probability distribution on the screen of where it's most likely that the particle will land. Okay, I would say particle, that the thing will land. It's not really a particle. So when they did that, they got the right answer. They said, okay, that works. We've got the right answer. We can determine that this particle is a probability distribution. That's why it looks like a wave, because the probability interacts in a wave. And they called it a probability wave. So you've probably, if you've known anything about quantum mechanics, you know that the big thing is the wave function, that everything talked about in terms of waves. Well, there's nothing actually waving. This isn't a physical thing that's waving or moving. It's not a physical thing at all. It's a mathematical thing. These are probability waves, not things that are, it's not a particle that's moving like a wave. It's a particle that isn't a particle. It is a wave. So if that was the case, now let's get to the point where they put the detectors in. These little red spots will be detectors here and here and there and there. Now, they have this probability, and when they detected a particle here, They made a measurement, right? When they made a measurement, the data stream has to tell them what it is they got. Well, the data stream tells them they got a particle because they made a measurement. After that, what can they do? A particle now has been found in this reality, headed that way. All it can ever do is do what particles do, right? They travel in straight lines unless acted on by some other force. That was one of Newton's laws. So they go in a straight line and hit right there because it's a particle. Up here, it's not a particle until it gets here. Here's where the measurement's made. You see? It's just probability until it gets here. Now the measurement's made. You see, here's the measurement screen. The measurement's made here, and the question is, where is the particle most likely to land? Well, it's most likely to land there in the middle, and then the other two white spots, and the other two white spots, and so on. And it lands there with that probability. You see the difference? This is where the measurement's made, so you get a particle here. No measurement was made here, so it's still probability here and here and here. You don't get a particle until it hits the screen. All right, now, here you get a particle here, and then it stays a particle. So that's why that works. Okay, well, the way it works with the delayed erasure is that it's still probability. All right, you haven't looked at the screen yet. We're doing this experiment. Let's say we're doing this experiment, and we make the measurement, but we don't look at the screen. Well, if we've got data here that says there's a particle, then we have to get light here and light here. Otherwise, it would be inconsistent, right? You have a reality that was inconsistent. But if we take that data, and before we look at the screen, we erase it. Now, where is there an inconsistency with a diffraction pattern? There is none. There's no data that says that there were particles. There used to be, but there isn't anymore. You know, somebody says, yeah, but there used to be data, and you say, prove it. It's gone. There isn't any data. So we don't have that data in here, and until we actually have that data available for people to look at, now the people don't have to look at it, it just needs to be in a computer or somewhere where they could look at it, then there would be an inconsistency if you didn't have particles. But if there is no data, then there's no reason to have particles. You go to the default answer, which is probability, and if you display the energy here and the probability when it hits, you get a diffraction pattern. You see, so even though they took that film out of the camera, when the experiment was done, there's nothing necessarily on that film because reality doesn't start until you get data from the system to you. You see, until you make the measurement, it doesn't exist. It's only potential. It exists as probability because the way the world works is everything is probability until you make the measurement. Until I look to the left to see that there's mountains there, you know, I don't see any mountains. There's no mountains there. I don't have any data on mountains. I look, I get the data, I take the measurement. Now there's mountains there. So, and this is a multiplayer game, so there's always mountains there for all of us when we look that way. And once one of us looks, okay, now there's mountains there. There can't be mountains there for me and, you know, palm trees and a beach for you. It's a, you know, this is multiplayer reality. We all have to agree on that. So if somebody looks and sees the mountains, then we all close our eyes, you know, and the mountains don't go away because when we look, probability is 1 that there's still going to be mountains there. All right, so that's what's going on. So Schrodinger talked about this in another form, you know. It was called Schrodinger's cat. I don't know if you've heard that, but it's the same thing. You know, he put, his thought experiment wasn't very nice, but he had these boxes. He had lots of boxes, and every box had a cat. And these cats, of course, didn't need to go to the bathroom or have their litter changed. They didn't have to be fed. These are magical cats that just exist, so it's a thought experiment, even if it is kind of cruelty to animals. He put them all in a box, and then inside the box, he put a thing that had poison in it, a glass that had poison in it. And there was a Geiger counter that would react when some kind of, say, alpha particle or something from a decayed, you know, a radioactive source would decay. And if that decay hit the Geiger counter would react, and it would break the vial, and the poison would be dispensed, and the cat would die. All right. Now, we know that randomness is what describes a source radiating. Sources only radiate randomly. Sometimes they do, sometimes they don't. There isn't any way to compute the sources about, to radiate a particle. And the particles go out in all directions. So the probability of a certain particle hitting this detector, which then opens the vial. So he said that you had all these cats, and what he was trying to do, really, he wasn't doing this seriously as much as he was trying to make a point about how the science works and how crazy it was. So he said, you have all the cats in the boxes with these arrangements, and you don't know whether a cat is alive or dead until you look at it, and indeed, until you open the box. He said, indeed, there are no dead cats or no alive cats. It's just unknown. It's just probability. You don't know until you look inside the box. So it's not that the cat, we think the cat's either dead or the cat's alive. It's a 1 or a 0. Those dots are on the film or they're not on the film. It's a 1 or a 0. All right, we did the experiments. The dots should be on the film. That's it. We believe that's it. And then when they're not, we go, oh, wow, what happened? It's a diffraction pattern. It should have been dots. He's saying they're not really anything on that film until you look at it and force the system to send you data that describes what's in this reality. And at that point, something shows up on the film. And what shows up on the film is a probability distribution, a random draw from a probability distribution that takes into account history. What has it been? What are the constraints on the problem? Because the idea is you can't create anything in the reality that is a conflict. Everything has to match. Everything has to work. Okay, so if there's data showing there's a particle, that random draw is going to be a flat probability like this of 1. You're always going to draw a particle when you look at it, because here's the data that says it was a particle. So now we've got data saying that this is the way it is. That's not going to disagree with it. Now the probability is 1 that what you get are those 2 dots. You see? But once you erase the data, could be, could not be, particles, could be something else. We don't know. Okay? And we know what it would have been if we hadn't erased the data, but we did erase the data. So there's nothing that says it's a particle. It drops back to the default answer, which is its probability distribution. So that's the way the world works. So if you understand it's a virtual reality and that we get data that defines what's in this reality when we make the measurement, then it's all perfectly clear why it works that way. But if you believe we live in a should we call it, an objective reality, then the experiment doesn't make any sense. You see, it's impossible. It can't happen that way. You can't have a cat alive and dead at the same time. A cat in an indeterminate state of alive or dead. You see, he made this thing because that was a ridiculous idea, and he was trying to demonstrate how crazy it was, that that's the way the world works. It works like that with photons. It works like that with cats. It works that way with everything. That's why in the big picture I said you could take a telescope and look, and what you get is some random draw from all of the possibilities that would fit the constraints of history and what we've seen other places and whatever. So those are the constraints, but there's often not just one answer that satisfies the constraints, and you'll get this random draw from those answers. And that's it. But then once it's here, now that's in our physical reality, it's in our shared reality. It has to stay. After that, seeing that thing becomes a probability of 1, because now it's here. The first time it looked, it could have been lots of things. So you see that the reality of what's there gets created on the spot from a random draw. Now we tend to believe, our culture believes that whatever's there was there. It's always been there, and when we look at it, we see what's there. But the material reductionism just doesn't work. There's so many things that it doesn't explain. It's got so many problems, and quantum mechanics is one of them. You've got all sorts of quantum mechanical events. Like I mentioned, you got tunneling, you got entanglement, you got lots of events, and in physics they call it non-locality. Basically what that means is it doesn't make any sense to them and they don't understand it. these non-local events. That sounds like it's not so bad, right? Non-local, just like there's not really a problem here. It's just this complementary principle. Everything's okay. But that's the problem. So if you look at some of the really best quantum mechanics physicists that we've had, and you'll see that they make comments like, no one will ever understand this. It's just weird science. It's impossible to understand, and we just have to let that go. See, that's kind of the attitude that science has. Well, if that's your attitude, if you believe it's impossible, it's going to be pretty impossible. Because anybody tells you anything different, it's like, nah, it can't be that way. You don't even allow that thought in. So that's kind of where they are. Whereas back in the first decade of this, they really were excited about it. This is a breakthrough. Reality is very different than what we see. Our old, Newtonian idea of something's there because it's fundamentally always been there is wrong. Our whole concept is backwards, but they didn't know what to do with it. They couldn't explain it. They didn't have any idea. Digital science was, 50 years away from even being thought about. Ideas of virtual realities wasn't anybody's vague idea. Computers were 50 years later before even they got invented, much less got to the point where you could generate a virtual reality. And people started thinking in terms of information as opposed to things are just always that way because that's the way they are. So the concepts that were required to understand this didn't actually start to bubble up to the surface until 50s and 60s and 70s, and then they were very basic, and we didn't actually have an idea of virtual reality until maybe 30 years ago, 25 years ago, when we started to think about it. And it's only been in the last decade that we actually see, hey, our computers keep getting faster and faster and faster. Where are they going to be in 100 years? Oh, we'll be able to do virtual realities about as good as this one, you see. Suddenly it becomes not such a crazy idea anymore. We can see how it works. You see, but back then, 1920, they had no way of seeing how it worked. They worked on it, and you can see lots of quotes from scientists of that day, which would have been, like Schrodinger and Heisenberg, Einstein, Bohr, and a half a dozen others, Eugene Wigner, and you'll see that they said that we realize that mind is primary here. Why? It's not until somebody develops the film, which brings it up so that people can look at it, right, that we get an answer. Well, what's so magic about people looking at it? What does that have to do with anything? But they realized that was fundamental because that's what the experiment told them. So they knew that consciousness was fundamental back at that time in the 1920s. And matter of fact, they even came to a point where they said, well, consciousness collapsed the wave function. And then they decided measurement collapses the wave function. Well, it takes a consciousness to make a measurement, and it takes a measurement to make information. But the key is information. It's not that consciousness collapses the wave function to a particle. That's what happens when you make this measurement. It's not that the measurement collapses the wave function to a particle. It's the creation of the information. The consciousness takes the measurement, which creates information. And if the information is here, now you can't have an inconsistency with the information. You see? That's why you can erase the information, and it reverts back to the kind of the original state. It's not about consciousness. It's not about measurement. It's about information. What does that tell you? It's a virtual reality based on information. I mean, it's perfectly clear, right? Yes?
What if you get information, and so it's here, and then what if everybody who knows that information dies? Does the information remain?
Nope. Information's gone. If the information's gone, it can change. So let's say that person with his telescope took that measurement, and there's a nebula there that's this and that way, and he mapped all that, he took the picture of it, and other people come in and they take the picture of it, and so on. But let's say after 10 people took the picture and they all saw the same thing and it was all like that, that whole area gets a disease and they all fall over dead and all the pictures burn in the fire and, et cetera. The information's gone. No information at all what's in that part of space. Now, sometime later, somebody else gets a telescope that's not burnt and they look up there, they take a random draw out of all the possibilities and that's what they get. And it doesn't have to be the same thing. You see? Because there's no information here. That's the same as the erasure experiment, right? That's a delayed erasure experiment. It's the same thing. So now they get something different. And now they didn't see that nebula. They saw a red dwarf or something because that was another one of the possibilities, and that's the draw they got. And now everybody else that looks after that will see a red dwarf. Information comes and goes. And when it goes, it's gone. So you see, that's the point. It's not the consciousness. It's not the measurement. It's the information is really what the key is here. Because this reality is based on information. And a good virtual reality can't have information in it that conflicts. You can't have information that says it's up, another information that says it's down, and it's both valid information because it can't be up and down at the same time. So if this one says it's up, then the probability that it's up goes to 1 when you look at it again. So the information is consistent. Yes, sir?
How can you have information without consciousness to appreciate it?
Exactly. You can't, you see. Information requires a consciousness. So consciousness is fundamental. True. Measurement is fundamental. If all the scientists, sat in deep holes with their eyes shut, we'd never do this experiment. The fact that they got out and made a measurement is important. But the critical element here is that they're creating information. And it takes a consciousness to create information. And the consciousness has to make a measurement in this virtual reality to create information that defines a particle in this virtual reality. You see? So all of them are involved, but the most fundamental of those three is the information. But yes, a consciousness is required. So we had, we have lots of different ways of stating that, but basically it's about information. If it was just about the measurement, you see, then once you made this measurement, the fact of erasing it later wouldn't make any difference. So it's not just a measurement. If it was just consciousness, you would say that, let's see, how would we isolate consciousness? If it was just consciousness, had to observe it, then once the consciousness saw that all the data was measured, it probably wouldn't matter that if that was it, then you'd have the answer. And it probably wouldn't change if you erased the data because the consciousness already was aware of it, but it does. So what's critical is the information, but just consciousness is required. If you read that little handout I gave you, the first one's about information, and it says that you don't have information without consciousness. And consciousness creates information and gives information and shares information and interprets information. So the consciousness has to look at the film and has to interpret what it means. Otherwise, there's nothing there. So you could develop the film. I talked about you develop the film to look at it. You could develop the film and put it in a box and not look at it for years, and it wouldn't make any difference. When you see it, it's going to give you that diffraction pattern if the data's raised. So that's the way this works. So this is quantum mechanics, and quantum mechanics became a science when they made the assumption that you represent a particle with a probability distribution. And their idea was we don't know why that should work, but we know if we do that, we can calculate the right outcome. And they got better and better over the years at calculating. So now quantum physics is a far cry superior to the quantum physics in the 1920s in their ability to calculate. But they've even given up the idea of understanding their weird science. And they're convinced that there is no explanation. When they're, but now we're going to solve that because science is going toward virtual reality, and obviously virtual reality supports looking at it from this viewpoint. It makes perfect sense.